So now is visible.
Yes, now
Yeah, yeah.
visible.
Okay, so the topic is yeah. So hi everyone, uh, Abhinandan this side,
Hi,
and
Abhinandan.
yeah, yeah, and
Hi,
with
Abhinandan.
me, I have two very brilliant student, Nivas and Ansuman. Yeah, the future
Hello,
researchers. Yeah.
Hi, hi, guys.
Okay. So today we'll discuss the very fundamental paper that is reducing the dimensionality of data with neural networks. This kind of paper, like this paper, gave a idea about autoencoders. I mean, nowadays we have MAE, like mass autoencoders, which can do a lot of reconstruction task very efficiently. But at that point, at that time in 2006, we don't have this kind of like more kind of beautiful optimizers, more kind of deep NN. So training deep NN was pretty much like hard task on that time. And also like we know that for the case of neural networks and DNN, the data is and the it's kind of it's not a kind of linear path. It's a kind of extreme non-linear path, non-linear kind of data that we faced. So and this paper gave a very much beautiful thing to actually train NN in a different kind of approach. Yeah. So let's start. Okay. So like here's the background. I mean before 2006, as I've discussed. The training, the high dimensional data is very much difficult to analyze. I mean, we have our first CNN, and after that, the CNN becomes a boom. I mean, the people are using CNN and doing everything, every task. But then after that, a clear shift happens. So, I mean, as the number of data are keep pretty much increasing, training stuff is become so much like difficult to do so, because of the many situations. Like we don't have optimizers, we don't have great gradient descent algorithms like on much depth level and so on and so forth. We have some data reduction technique on that time. I mean the PCA was the standard dimensionality reduction technique that we have to deal with the like extreme dimensional data. But there's one problem with PCA, like the principal component analysis. The thing is that PCA is linear and it cannot learn non-linear data, non-linear manifolds. And we all know that for the case of NN and DNN, the data that we deal with is non-linear, is too much sparse and vague, etc., etc. So, like training the DNN was existed that I have talked about, but it was extremely difficult to train. Now, see, like you can see a pretty much like roadmap. We have high dimensional data, then we need to have a compact representation for training those high data into efficient manner, but we don't have enough capability. We have PCA, but it's too much linear to work on. So how can actually work on? So a basic questions that this beautiful robot asking, like can DNN learns a compact non-linear representation of data? Now here's the fact. Then after that in 2026 this paper came by Geoffrey Hinton and his co-author, and they proposed a kind of new architecture, autoencoder, for learning image representation with high dimensional data. So they have proposed this kind of architecture that like will come later. So like now a basic questions: what is autoencoder? Well, by the name itself, you can actually see autoencoder means auto plus encoder. So there's a two simultaneous things that happen with an image in this kind of architecture. The one is encode. So when the image goes into encoder, the encoder encode that image and create a compact latent representation of that image. You can see latent representation is kind of like embeddings, a compact embeddings of image. I mean, lots of tensors and matrices, so on and so forth. And then when we pass this latent representation into decoder, then this decoder can look into this latent representation and can reconstruct the same image as the previous image. So this kind of architecture that they have proposed, and that time it was like a innovative idea. I mean, see, I mean, reconstructing an image from a dense embedding was pretty much effective and pretty much elaborative at that time. So like here's the like basic mathematical equations where x is the input image, this image, and f theta is the encoder that you have representing. Z is the latent representation, and then when we input this Z into decoder, that is Z5, we have X dash, that is the reconstructed image. And like we all know, one of the craziest way on which we can able to make neural networks to learn any new stuff, that is by minimizing the error. And in this way, the error is the original image, like the error is between original image as well as this reconstruction image. So we use MAC to minimize the loss, and then we have that like reconstructed image. Now, how they actually do it? So they have done a pretty much important stuff. So you can see in encoder there's an image of a like face. So they initially take a linear layer of 2000 and pass through it. So we are now pretty much uh, lessening the representation embedding. So initially, let's say this image is worth of like 2 to 4x 2 to 4, and we are passing through 2000 layer. So this will give roughly around a large kind of embedding of this image into this only this specific portion. But now we don't want to work with this large portion. We want to work with a small portion of that image. So then we reduce to 1000 layer, then we reduce to 500 and then 30. Now this 30 is the latent representation here. This is the latent representation. So 30 is the code layer and that have the compact representation of this entire image. Now we do the same stuff with decoder and then we reconstruct an image. Now see the difference. This is the original image and this is the representation image. So like this is the X and this is the X dash. Now we are dealing with some kind of objective like this minimizing objective and we are like reducing the distance and now like after pretty much fine tuning we have this kind of stuff. So see the different like the original and the reconstructed image is pretty much same. So like that's a kind of deep autoencoder that proposed onto that like paper. So yeah, I mean the middle is
So,
yeah you can ask
yeah, I've got a question. So we had 2000, and then we
shrink
compacted it, compressed it to just
yeah
30.
yeah
So the bottom image, bottom face is the original, and the
yeah
upper face is the final
yeah like
result.
reconstructed result yeah.
Yes, and after fine tuning, we can actually make the face
Yeah,
out
yeah,
better.
exactly.
So this is the lossy process. However, we can preserve most of the quality, but reduce the size by 10, like more than.
Yeah, I mean, you can do. Yeah, exactly. Your question is right. I mean, uh, why not like why 30? Why not 15? Or why not more than that? We can do that. Say like they have also done in ablation studies. Uh, and after doing some ablation studies, they propose that like 30 give us a kind of compact representation. So let's like think with 30. But nowadays we have many papers that also proposes 16. So like there's a recent paper in ICML 2026. They propose like instead of having this large embedding, if we compress that image with only 16 tokens, so we can have better representation. So yeah, I mean things are pretty much evolving. In 2006, it was a kind of like new idea to work with that, but nowadays, like the thing has shifted, and people are like exploring beyond 30, kind of more stuff.
So they
Yeah, further
further
compressed it
compressed
exactly.
it.
Yeah. Okay. So like now, okay. So here's the fact. I mean, I have talked earlier that initially it was very much hard to train DNA. And there are various reasons for that that we also talked. The first is like vanishing gradient. So there are some two concepts that really irritate the AI nerds. That is exploding gradient and vanishing gradient. And the controlling of these two gradients is pretty much like effective, like pretty much important task. Like if we want to train any NN, then we need to control this vanishing gradient as well as exploding gradient. Now, at that time, we don't have such kind of methods to control this vanishing gradient problem. Then we also have problem with poor initialization of weights. Nowadays, we initialize weights in pretty much effective manner, but that time we don't have such kind of methods to do so. And also, our optimization objectives got stuck. Nowadays, we have pretty much everything. Like we have Adam to train DNA. I mean, in pretty much effective way. But that time, the optimization is pretty much a kind of big problem to solve with. And also like if you're familiar with gradient descent, so in gradient descent, like when we try to fix AI model, we apply gradient descent, and in gradient descent, we need to consider global minima as well as local minima. And at that time, we don't have any kind of like good optimization start like policy, good kind of like controlling, good kind of stuff to control the vanishing gradient. So that's why,
Abhinandan,
yeah, hello,
you're audible.
hello, hello,
Yes,
Yeah,
yes, now you're
okay,
audible.
okay,
now
okay.
it's on.
Like, yeah, I mean, I have been discussing this thing. So, okay, it's like I have been discussing about gradient descent. So, like nowadays we train DNN with like
Yes,
gradient
yes.
descent, but and also with gradient descent we have better optimizers, better loss functions. But that time it was a pretty much hectic task to train in from scratch. So, like we have problem with
RNW
so like
parts
we have problem with random initialization, then poor gradients, and then hence to like no learning of that model. But now,
You could I ask you what was the problem with the random initialization back
yeah,
then?
the initialization weights. I mean, see, I mean, when we train any NN, so in NN we have weights and biases, and nowadays we have like proper methods
Yes.
to initialize weight to train any NN from scratch. Like we have various methods, like proposed method. But that time it was not. It was a kind of hectic task to look into. So that was also kind of a new.
So couldn't they do this random initialization? Do we not do random initialization
Sorry.
even now? Of course. Did they not do random initialization back then? I mean, random initialization is the
Yeah,
way right
I
now,
mean it's a kind
right?
of way that we do. I mean,
So what
yeah,
was
the
the
problem
problem back
is not a kind of single problem. It was a combination of whole problem. It was a combination of not having proper optimization strategy. It was a combination of having like the not proper training strategy to have to conquer the global and local minima. So this kind of and also some kind of competition problem. So the whole problem got stuck together, and that makes pretty much like bad thing to train in. So not a single, but combination of everything. Yeah, yeah.
then? Okay, okay.
Now, now, yeah. I mean, I've been talking about this. See, so I have discussed that we have back then we have problem with optimization, we have problem with bad local minima and random aces and stuff. But what this paper actually do, this paper like suggested as a unique way to train in. Now, what is that unique way? They have used RBM. or restricted Boltzmann machine. Uh, in Boltzmann machine, it's kind of like idea like like old school in where we do have to train like 2 3 layers of neural network, like pretty much simple neural network. So that time we used Boltzmann machine in which the the visual layer as well as hidden layer can interchange, like can interact with each other. See, I mean here in this image you can see like V1 interacting with V2 and also like hidden layers H1, H2 and H3. So that so like the Boltzmann machine gave us an abstract idea about training NN back then, like the old school NN. But now this was suggested RBM, like restricted Boltzmann machine. And how like so like what is restricted? So they have done this. We are not connecting the V1 layers, the V's layers, and also the H layers. So like RBM imposes a restriction. See, and what restriction? No visible connection, no hidden connection. So there is no connection in there. That's how they have restricted the primary concept of like Boltzmann machine, and then they have like make this training like possible. But how possible? See, we have input image, we have like 2000 layers. So they have utilized RBM here. Also, they have utilized RBM in this phase. Also in this phase, also in this phase. So imagine a scenario. We have RBM, like we have trained RBM here, we have trained RBM here, we have trained RBM here, and we have trained RBM here. But what if we stack them together? So after stacking them together, we can do like gradient descent in pretty much important, like easy way. So that's a kind of new trick that they have like proposed. I mean, we can stack multiple RBMs and we can then like helps network to learn more stuff out of it. Like that's how like things got pretty much interested. And this approach later known as greedy layer-wise pretending that is also like used in like today's various stuff like layer-wise pretending. That's the kind of pretty much important like interesting thing. Yeah, I mean that's the kind of like new stuff that they have done in this paper. I mean, it's kind of like main crux of this paper. I mean, we have seen that like initially the training was completely like sucked, but now but after that, but after adding RBM, it was smooth and stuff. So yeah, I mean that's the kind of like basic thing that I've done. And as a result, like if we see, we have better reconstruction, we have better visualization, better like retrieval and compression stuff. So I mean now so we have discussed like initially PCA was only working on linear stuff, but nowadays like after this paper, we can also like say that yeah, I mean DNN can be done and in non-linear way, and that outperformed the standard PCA. So like that's the like kind of like basic autoencoder that they give. Now, if we go through the timeline, so what is the aftermath of it? So when they proposed this autoencoder stuff, then in 2008, there's another like in 2006 also there's another paper by Andrew Nang. I mean, you also know this guys, this guy. I mean, and he proposed sparse or autoencoder, and I mean, yeah, sparse autoencoder, and
SA,
I
yes,
mean, we
yes.
don't have the paper of it, but like I mean, he was okay. So like here's the kind of interesting story. Like I mean, while he was in Stanford, like teaching this deep autoencoder, he asked, "What if we can change some of it?" And in class itself, he discovered sparse autoencoder. So yeah, I mean, I have his class notes, so like I'll send. So from deep autoencoder, we have sparse autoencoder, and then in 2008, we have denoising autoencoder. And then in 2013, we have VAE, and then MAE, like master autoencoder, then JPA. I mean, uh, Ansuman, you have been talking about world models, right? So, like, yeah, yeah, like, exactly.
Yes, yes, yes.
So,
Joint
like,
embedding. Yes, yes,
JEPA, Joint
yes.
Embedding Predictive Analysis, was the first paper in 2023 that gives an idea about world models. And then the progress is, like, still going on in 2026 also. Yeah, Joint Embedding Predictive Architecture. Yeah. So, like, it's kind of like pretty much everything that we have. I mean, this is it. I mean, we have some kind of thing, and now we have everything.
Yeah, this was fun to know. I didn't know that this literally evolution from 2006 to right now
Yeah,
was that for the entire basis
yeah. I
of
mean,
CV.
the funny fact is like in science, everything is interconnected. I mean, to know a fundamental stuff, we need to go back to scratch. So the things are going crazy right now. It's too
Yep,
fast, man. I
developing too
mean,
fast.
it's going too fast.
Yeah,
I mean,
we can't keep
there's
up.
the one thing. I mean, we can't keep up with all the directions, but we can keep up with one single direction. So yeah, true.
Yeah,
Yeah,
true.
Yeah, it's not that all significant things are moving fast at the same pace. Lots of things are moving fast, but the evolutions are
yeah,
still
mm,
really
true.
sparse.
True
Like,
evolution is sparse right now.
like,
Yeah, I mean, people are doing
mm,
things. I mean, you also know that like people are doing like doing things, but the fundamental papers are come at a very long time, like JPA, then VAE, then MAE,
mm,
then like variation like denoising autoencoder. So fundamental things come in a very very gap way, but people are doing like the non-deep research in pretty much fast way. So yeah, I mean I think people are
exactly.
mostly running
Yeah.
behind buzzword right now.
So, did you hear
Yeah,
about
sorry,
that
sorry. Yeah,
Anthropics?
sorry.
Hello? So, did you know about that
J
J
paper.
paper by
I
Anthropic?
mean, like, what is this paper?
Elaborate.
Yeah, so basically they found a space in the neural network of their Opus model where the model actually stores the important. It's called J space paper, the important stuff
Okay,
like the core stuff. So if they changed something like from France to Japan, or if
okay,
they changed these terms in there, then the model output completely changes. However, the internal part, like it's like people are calling it the brain of the model. So everything is compacted down to that space, that little space. This I think this is a pretty big thing because it means that you could essentially just compress information and you know compress it to
yeah. I
such a
mean,
small
it's another
layer.
like news, and the things are like, yeah. I mean, things are pretty much exploding right now. Like you mentioned about J paper. I mean, yeah. I mean, I think the focus is shifting in a compression right now. I mean, the people are trying to do compression with various stuff. I mean, with language, with vision, with other kind of stuff. And according to me, I guess the comparison is the future. I mean, see, in future or right now, no one like uh, everyone don't have large kind of clusters of GPU to train a kind of model and so on and so forth. Yeah.
Mm,
So like,
exactly, exactly.
yeah,
So like the Qwen
yeah,
3.627b, the Gamma 431b, these I mean even leaving them aside, liquid AIs, small language models, these are kind of getting very very fast, and that one bit bonsai models, these are getting fast. And since Thinky Machines released
yeah. I used to see
entirely
that.
new
Yeah,
architectural model by weak links. Yeah, exactly. It's not even based on the distillation of various other models like these Chinese models are made like. So we are doing a lot of stuff
It's pretty
which
crazy. I
is pretty
think
crazy right
like
now.
yeah, I mean uh, we also need to pace up right now. I mean, specifically for India. I mean, I think India is lagging behind in AI race. It's too. I mean, only we have Servam AI, right, to actually look into it. Yeah, but they're also
Yes,
mostly in voice focused.
yes.
I mean, we do really have great
I mean, in India, nobody is into research and finding new things. They are
copycat.
trying to make
Yeah,
money
copycat, I
more out
guess.
of it in an
Exactly.
instant way. Yeah, yeah. They want the money so instant in a year or something. They aren't doing any research to find.
I wouldn't say that Indian things research is
Yeah,
copycat. I mean, have you looked at
yeah.
Chinese models? They copy American models,
Yeah,
then
I
they
mean,
make
But
better
recently,
models than
okay,
them.
yeah, but the issue is that
okay. I mean,
India
we
doesn't make it
can
better.
actually cross finger into that. I mean, the things will come and so on and so forth. I mean, yeah. Recently, Ansman, did you see that message? I mean, there are I think 25,000 Chinese account that signed in on Claude, and they distilled how Claude actually behave, and they like copy exactly
Yeah,
things. Yeah,
exactly, exactly. And then
exactly,
suddenly, Kimi releases their K3 model.
man. I mean,
That beats everything.
yeah. I
No,
mean,
no, this is seriously
I
good.
have.
They seriously good. They took
I
the
mean, I have
knowledge and they
like I have been
improved
going through
it.
this the
Yes.
some kind of like prototype of Kimi K3, and actually they're like did a great job. I mean, you can do a lot of good things. I mean, creating
Exactly,
games
exactly.
with physics kind of simulation, real physics simulation, and so on and so forth, going crazy, man. I mean, these
Mm,
Chinese models are going crazy.
exactly.
Cross finger that someday we'll also have big AI lab, big AI startup lab.
I do not think personally that we'll have a big AI labs, and I do not think we should focus on big AI anyways.
Yeah, it's
It's a lot
cost.
of costly things, and I think
Yeah.
we should support open source.
Yeah,
Like
I mean,
support
open
open
source
source,
is.
be open instead
But
of
nobody
making
is
I
gonna
friends
make
think.
like.
money in the open source.
Hmm?
It's all about money at the end. If it's an open source, not many people make money.
I
Nobody would
mean,
try that.
No, exactly. I'm saying we
I
should
think the
not even
fact
try
is
for
we'll
foundational
have to
language
have
models.
Yeah.
We should
one
be
AI lab
completely open.
that are really effective. I mean, see, US, China have their like US have OpenAI, Anthropic, then Gemini. China have Kimi, then Manus, then Quinn, DeepSeek, exactly. But
Deep sea.
India, we
DeepSeek,
yeah, in
Yeah.
India we don't really have. I
Quen.
guess if we have one, two, those are performing really good, then it's kind of like balanced approach. See, I mean, we also have to like innovate, right? I mean, the fact is like Answan is saying open source. Yeah, I mean, we can rely on open source, but the fact is like open source can be done on certain limitation way, but not on completely whole stuff. Uh, some closed source stuff also important for country. So that's like yeah, I mean most of the like Queen I think Queen is half closed, right? I mean not fully open.
No, no, no. Currently, it's purely open. People are discussing that they might go close for
Yeah.
3.7, but right now it's open.
Yeah,
None
but
of them are closed.
I don't know why, but yeah, I mean but also yeah, I mean stuffs are going crazy, man. We can look into it further. Yeah.
Yeah.
Okay.
Mm.
Yeah.
So this was a
Yeah.
great session, Abhinandan. This was a great session. This was the first time I got to know that RBMs were the ones
Yeah, I
that
mean
changed the neural network
the fact
architecture.
is like
Me too. Same.
RBM was pretty kind of like hectic topic for me. When I start learning about RBM, to learn RBM, you have to learn boson mission. Then you have to learn some of the energy concept like physics simulation, and then you can understand RBM. So it's kind of like total messy stuff. So yeah, but yeah, I mean we have enjoyed it. Yeah.
Exactly.
Okay, then we'll meet again. I think in the
Yeah.
next
Yeah.
week also we'll have.